In this class, we are going to prove that HK is a subgroup of G provided HK is equal to KH. Obviously, H and K are already subgroups of G. But let us recall what exactly HK sets look like. So HK is actually collection of product of elements of H and K. That is, it is H multiplied by K, where this H is from H and K is from K. Similarly, we have KH. Now in KH, first of all, we'll have element of K and then element of H, where K is from K and H is from H. Now in order to prove HK is actually a subgroup, we are going to take the help of one step subgroup test. So what does it say? Given a group G, given a set H, how to show that this H is a subgroup of G? First of all, we need to show H is non-empty. Then we are supposed to show H is a subset of G, and then finally we will prove the condition of subgroups, that is taking any two elements of H and proving AB inverse lies in H. So in order to prove HK is a subgroup, first of all we are supposed to show that HK is non-empty. Now the question is, why HK will be non-empty, right? Note that HK contains collection of products of element of H and K both. So if you have an element of H, if you have an element of K, simply take the product and you get an element of HK. Now, which are the guaranteed elements that are present in both the sets, in fact in both the subgroups H and K? As we know, subgroup itself is a group, and group is always a non-empty set, and it always contains identity element. By using that fact, this H and K will definitely contain identity element for sure. So what we will say, note that this E into E is an element of HK. This first E represents elements of H and the second E represent element of K. But as we know, E into E is nothing but E only, so this implies E belongs to what? HK, and therefore HK is non-empty. No issues for subset. Clearly HK is a subset of G, as H and K are subsets of G. So that will definitely happen, and obviously a binary operation is there in the set G. Thus the multiplication of H and K will always be an element of G. Now as we have to prove one step subgroup test, I will take two elements of HK. So I will say let A comma B belongs to HK be any elements. But as we know, element of HK is the, element of HK takes the form element of H multiplied by element of K. So I will write it as H1 K1, and similarly I will write B as H2 K2 for some H1 H2 belonging to H and K1 K2 belonging to K. Now as we have to show AB inverse is the element of HK, I will start with AB inverse. So we will say consider AB inverse which is actually equal to, put the value of A, put the value of B there. So this will be H1 K1 multiplied by H2 K2 raised to what? -1, which is further equal to, now we can always use Shoe-Sock's property. So H2 K2 inverse is actually nothing but K2 inverse and H2 inverse. Now remember that we have to show this element lies in HK. So when the element will be in HK, if it is written as product of element of H and K, right? So as we notice in AB inverse we already have an element of H here. So if anyhow we get an element of K on this side, then we can conclude that this is an element of HK. But the problem here is this K1 and K2 inverse is an element of K, no problems for that, but this actually H2 inverse is an element of H again. So in order to prove AB inverse belongs to HK, definitely we have to take the help of the given thing, that is nothing but HK is equal to KH. Now as we observe, the element here is actually nothing but product of two elements. I mean, I will treat K1 as our first element and the second one I will treat K1 K2 inverse as our first element and the second one is H2 inverse. So this K1 K2 inverse is an element of K here and this H2 inverse is an element of H. Thus this element lies in what? KH. But as we know, KH is nothing but HK, so this fact we have to use. So I will say, let us call it as 1. So as K1 and K2 both are members of K, that is what we have written here. So this will definitely imply that this K1 K2 inverse is a member of K. Okay, this follows from what? Since K is a subgroup of G and we have used the one-step test. Now also we have H2 belongs to H, right? But this will again imply H2 inverse belongs to H itself. Again the same reason, H is a subgroup of G. So here we are taking the help of a second condition in two-step subgroup test, that is A belongs to H always implies A inverse belongs to H. So what will happen is K1 K2 inverse multiplied by H2 inverse will now be an element of KH, which further implies this K1 K2 inverse multiplied by H2 inverse is an element of KH. But our KH is nothing but what? HK. Therefore this element K1 K2 inverse dot H2 inverse is an element of HK. Now since it is an element of HK, we can write it as a product of element of H and element of K. So this implies this K1 K2 inverse multiplied by H2 inverse can be written as product of element of H and element of K. So I will call element of H as H3 and the element of K as K3. Let us give it a name, we will call it as 2. Now we will use 2 in 1. So if we use 2 in 1, what we will get? We will get the value of AB inverse. So our AB inverse now will look as H1 multiplied by H3 multiplied by K3. If we observe it properly, it is actually nothing but multiplication of an element of H and the element of K. The element of H is nothing but H1 H3 and the element of K is nothing but K3. So therefore we have expressed AB inverse as product of element of H and the element of K, and therefore this belongs to HK. Let me mention the reason. This H1 H3 belongs to H as H is a subgroup of G. We have used the first condition, you can say, of two-step test. A comma B belongs to H implies A multiplied by belongs to H, right? Here H1 and H2 were members of H. Therefore H1 was a member of H and H3 is also a member of H, so this H1 H3 is also a member of H, right? And therefore HK is actually a subgroup of G, because we have started with any two elements of HK and we have shown that AB inverse also lies in HK. Thus by two-step test, HK is a subgroup of G.